Slapton Sands, Devon, England, May 3, 1944, 8:15 hours. Lieutenant Commander Dennis Cambell stood on the beach watching Exercise Fabius, the final full-scale rehearsal for D-Day. 30 landing craft, tank, LCT, had just hit the shore. Their mission, drop bow ramps, disgorge tanks, secure the beach. Simple. Rehearsed 100 times. LCT 947 grounded first. Engines cut. The bow ramp, a massive steel door weighing 3 tons, began to lower. It dropped halfway, then jammed. Stuck. Inside, 4 M4 Sherman tanks, 40 tons each, 160 tons of American armor trapped behind a stuck ramp. The tank commander's voice crackled over radio. "Ramps jammed, can't deploy." Through binoculars, Cambell watched LCT 947's crew frantically work the hydraulics. Manual override engaged. 4 sailors straining at lever arms. The ramp wouldn't move. LCT 863 beached nearby. Same problem. Ramp jammed halfway. LCT 712 jammed. LCT 534 jammed. LCT 289 jammed. Within 30 minutes, 22 out of 30 landing craft had failed to deploy their ramps. The beachmaster approached Cambell. "Failure rate is holding at 73%, sir. Same as Exercise Duck. Same as Exercise Jansen." 73%. 5 weeks until D-Day. If 73% of ramps jammed on June 6th, tanks couldn't leave the boats. Infantry advancing without armor support would be slaughtered. The invasion could fail before it began. Cambell walked to LCT 947, climbed aboard, examined the jammed mechanism. Hydraulics, functional. Motors, working. The ramp itself, undamaged. He knelt beside the hinge assembly, ran his finger along the main hinge pin. It came away covered in wet sand. That was the problem. Beach sand, just a few pounds compressed into the pivot mechanism, created enough friction to prevent a 3-ton steel door from moving. The LCT design had no protection against sand infiltration. No seals, no guards, nothing. 6,000 of these vessels were staged in England, waiting to carry the invasion force to Normandy. Cambell checked his watch. May 3rd. D-Day, early June, weather permitting. Approximately 5 weeks to solve a problem that threatened the largest amphibious invasion in history. The problem, sand jamming ramp mechanisms on 73% of landing craft. The solution, when his engineering team found it, would be a spring-loaded striker bolt. Parts cost, approximately £2 sterling. That bolt and the engineers who installed it on 6,000 ships in 3 weeks would save D-Day. This is not a story about heroism under fire. This is a story about what happens when a $3 billion operation depends on 6,000 machines that fail 3 times out of 4. When the fate of the free world hangs on bow ramps that won't open because nobody thought about sand. This is the story of how D-Day was saved not by generals or grand strategy, but by a team of engineers with wrenches, springs, and 3 weeks to modify an entire invasion fleet. This is the story of the bolt that saved D-Day. Brooklyn Navy Yard, New York, 1942. The landing craft tank, LCT, was designed to solve an impossible problem. How do you land a 40-ton tank directly onto a hostile beach? Conventional landing craft couldn't do it. Too small, too light, couldn't carry the weight. The LCT solution, a flat-bottomed steel vessel, 120 feet long, designed to drive straight onto the beach, drop its bow ramp, and let tanks roll directly onto shore. Specifications: length, 119 feet. Width, 32 feet. Displacement, 280 tons, fully loaded. Cargo capacity, 5 to 6 Sherman tanks or 150 tons of vehicles. Crew, 12 men. Maximum speed, 8 knots. Not fast, not elegant, but capable of beaching and deploying armor directly onto enemy shores. The bow ramp mechanism, the critical component. A 3-ton hinged steel ramp at the bow. Operating principle. 1. LCT beaches, bow grounds on sand or shingle. 2. Crew activates hydraulic release system. 3. 2 large hinge pins, 1 on each side, withdraw from housings. 4. Freed from pins, ramp drops forward by its own weight. 5. Tanks roll out onto beach. 6. LCT retracts, ramp raises, vessel withdraws for next load. In calm water on a clean concrete ramp, in ideal conditions, The system worked perfectly. Between 1942 and 1944, Allied shipyards built approximately 2,400 LCT vessels. By May 1944, roughly 6,000 landing craft of all types were assembled in southern England for the Normandy invasion. The LCT was the workhorse. Without functional LCT, you couldn't land armor. Without armor, infantry couldn't break off the beaches. Without breaking off the beaches, the invasion fails. Everything depended on those bow ramps opening. The first warning, Dieppe, August 1942. Operation Jubilee, the catastrophic raid on Dieppe, France. Canadian and British forces suffered 60% casualties in 9 hours. Among the many failures, landing craft ramp malfunctions. British after-action report, September 1942. Multiple LCT experienced bow ramp failures. Mechanisms jammed with beach material, preventing timely tank deployment. Infantry units forced to wait behind immobilized armor, resulting in significant casualties. Engineers investigated, found sand and small stones lodged in hinge mechanisms, recommended protective covers. The recommendation was filed, then forgotten. Why? Dieppe was considered an aberration, poor planning, bad execution, bad luck. Production of LCT continued with no design changes. 1943 to 1944, the pattern emerges. As Allied forces intensified amphibious training, reports began accumulating. Exercise Pirate, Scotland, March 1943. LCT ramp failure rate, 31%. Exercise Janssen, Devon, 1944. LCT ramp failure rate, 31%. October 1943. Failure rate, 44%. Exercise Duck, Slapton Sands, January 1944. Failure rate, 58%. Exercise Tiger, Slapton Sands, April 1944. Failure rate, 68%. Exercise Fabius, May 3rd to 8th, 1944. Failure rate, 73%. The rate was increasing, not decreasing. Why? Training exercises were becoming more realistic. Beaches selected to simulate Normandy conditions. Coarse sand, shingle, tidal variation. The more realistic the exercise, the more ramps jammed. The engineering community knew. Captain Joseph Vaghi, U.S. Navy Bureau of Ships, Washington. Throughout 1943 and early 1944, we received consistent reports of LCT bow ramp malfunctions. The cause was clear. Sand and shingle infiltration into hinge assemblies created friction exceeding hydraulic capacity. We issued technical bulletins instructing crews to clear debris before ramp deployment. This proved impractical under combat conditions. The problem required an engineering solution, not procedural workarounds. But by spring 1944, 6,000 landing craft were built, loaded, staged in England. Redesigning the ramp mechanism fleet-wide, impossible, would require a year. The Navy accepted the risk. Crews were trained on emergency procedures. If ramp jams, use manual override. If manual override fails, reverse tanks out through rear cargo doors. Backing a 40-ton tank out of a landing craft under enemy fire, not ideal. But time had run out for better solutions. May 3rd to 8th, 1944. Exercise Fabius. The final dress rehearsal. Full-scale simulation of D-Day. 73% ramp failure rate. Lieutenant Commander Dennis Cambell, Royal Navy Liaison Officer assigned to Amphibious Operations Coordination, watched the disaster unfold. Cambell wasn't a newcomer to amphibious warfare. He'd participated in North Africa landings, 1942, Sicily, 1943. He'd seen landing craft failures before, but never at this scale. 73% meant if D-Day replicated Exercise Fabius, roughly 4,400 landing craft would beach with jammed ramps. Thousands of tanks trapped. Tens of thousands of infantry pinned down without armor support. Omaha Beach, already expected to be the bloodiest landing, would become a slaughter. May 8th, final day of Exercise Fabius, Cambell made a decision. He would solve this problem. He had 5 weeks. Cambell had identified the enemy, sand in the hinges, but 6,000 ships were built, loaded, and waiting. Redesigning the ramp system, impossible. There was no time for sophisticated engineering. He needed something simple, fast, and deployable across an entire fleet in weeks. What his team developed would be so crude that senior officers would initially reject it as unworthy of the Royal Navy. But sometimes crude solutions save the world. Portsmouth Naval Engineering Facility, England, May 9, 1944, 0600 hours. Lieutenant Commander Dennis Cambell wasn't supposed to solve the ramp problem. His official role, Royal Navy Engineering Branch Liaison to U.S. Navy Amphibious Forces, coordinating British and American landing craft operations. But Exercise Fabius had shaken him. Cambell had engineering credentials. Before the war, marine engineer at Glasgow shipyards, specializing in hydraulic systems and heavy machinery. Commissioned September 1939, assigned to landing craft development because of his technical background. He understood LCT design intimately. He'd reviewed the blueprints, understood the hydraulic systems, knew the ramp mechanism's theoretical limits. What he hadn't understood until May 3rd was how catastrophically those limits would be exceeded under realistic beach conditions. May 9th, Cambell requested a meeting. Admiral John Leslie Hall, Jr., commander of U.S. Naval Force O, Omaha Beach Assault Force, received Cambell at Portsmouth headquarters. Cambell presented the problem. Sir, 73% ramp failure rate. If this replicates on D-Day, we won't get armor off the beaches. Hall. Commander, we're 5 weeks from the largest amphibious operation in history. Every vessel is staged, every crew is trained, every loadout is finalized. You want to start modifying landing craft now? Cambell. Sir, I want permission to develop a solution. Give me 72 hours to prove it's feasible. Hall studied the Exercise Fabius reports. 73% failure. The number was undeniable. 72 hours, Commander. But understand, if your solution requires extensive redesign or delays the invasion timeline, it won't be implemented. We don't have time for perfect. We need achievable. Cambell. Understood, sir. Achievable is exactly what I'm proposing. May 9th to 11th. The investigation. Cambell assembled a small team. Lieutenant Robert Fraser, mechanical engineer. Chief Petty Officer William Hughes, hydraulic specialist. 3 Royal Navy machinists from Portsmouth workshops. They commandeered LCT 947, one of the boats with jammed rams from Exercise Fabius, and began systematic analysis. Hour 1 to 6, understanding the mechanism. The bow ramp was held closed by 2 cylindrical steel pins, each 4 inches in diameter, running through the ramp hinges into hull-mounted housings. To deploy the ramp, 1. Hydraulic actuators push the pins outward. 2. Pins withdraw from housings. 3. Ramp, freed from pins, drops forward by gravity. 3-ton weight ensures this. 4. Tanks exit. Simple mechanism, should work reliably. Hour 6 to 12. Identifying the failure mode. The team disassembled a jammed hinge assembly. Finding: beach sand, fine, wet, compressed by seawater and ramp pressure, had infiltrated the tiny gap between pin and housing. Just 2 to 3 ounces of sand, compressed into a paste, created a friction lock. Hydraulic pressure, 800 psi, pounds per square inch. Calculated friction resistance from sand, 1,200 to 1,500 psi. The hydraulics couldn't overcome the sand's grip. Hour 12 to 24, evaluating solutions. The team listed possible fixes. Option 1, increase hydraulic pressure. Requirement, 2,000 psi minimum. Problem, requires replacing entire hydraulic system on 6,000 boats. Time needed, 6 months minimum. Verdict, impossible. Option 2, protective seals around pins. Requirement, flexible seal that handles 3-ton dynamic load. Problem, no existing seal design meets requirements. Time needed, 3 to 4 months design and testing. Verdict, impossible. Option 3, different pin material, stainless steel, reduced friction. Requirement, 12,000 new pins, 2 per boat. Problem, manufacturing time 2 to 3 months. Verdict, impossible. Option 4, redesigned hinge with enclosed mechanism. Requirement, complete ramp redesign. Problem, would require dry docking all 6,000 vessels. Verdict, impossible. Every conventional engineering solution required time they didn't have. Hour 30, the breakthrough. Chief Petty Officer Hughes was examining the pin for the 20th time. Sir, he said to Cambell, we're thinking about this wrong. Cambell, explain. Hughes, we're trying to push the pin out smoothly against sand resistance, but the pin doesn't need to slide out smoothly. It needs to break free from the sand's grip, just enough for gravity to take over. He demonstrated, gave the pin a sharp rap with a wrench. The pin shifted 3 millimeters, the sand's grip broken. Once it moves even slightly, Hughes continued, the ramp's weight will drop it. We don't need more hydraulic pressure. We need impact force to break static friction. Cambell understood immediately, like hitting a stuck bolt with a hammer. Hughes, exactly, sir, but you can't have a sailor with a hammer running around a landing craft under fire. Cambell, what if the hammer is built into the mechanism? Hour 36 to 48, design. Lieutenant Fraser sketched the solution. A spring-loaded striker bolt mounted parallel to each main hinge pin. Mechanism, 1. Compressed heavy spring behind striker bolt, 2. Striker bolt held by catch integrated into existing hydraulic trigger, 3. When hydraulics activate to release main pin, they simultaneously release striker catch. 4. Spring drives striker bolt forward with sharp impact into main pin. 5. Impact shock breaks sand's friction grip. 6. Hydraulics then push freed pin out. 7. Ramp drops. The elegance. Simple. Bolt, spring, mounting bracket, release catch. Cheap. Off-the-shelf components, approximately 2 pounds, $8 per boat. Fast to install, estimated 45 minutes per vessel. No redesign of existing systems required. Uses existing hydraulic trigger, no new controls needed. The physics. Striker bolt didn't need to move the pin, just break the sand's static friction grip. Impact force from compressed spring, approximately 400 pounds concentrated on 1 square inch contact area, delivered in milliseconds. That sharp shock would fracture the compressed sand structure. Once static friction broke, existing hydraulics could push the pin out. Hour 48 to 72, prototype and test. Portsmouth Machine Shop fabricated 2 striker bolt assemblies. May 11th, 0600. Installation on LCT 947. May 11th, 1400. Beach test at Slapton Sands. LCT 947 beached. Hydraulic release activated. Clang. Sharp metallic impact. Striker bolts firing. Smooth hydraulic hum. The ramp dropped perfectly onto the beach. 32 seconds from hydraulic activation to full deployment. Test repeated. Successful. Repeated again. Successful. 5 consecutive successful deployments. May 11th, 1800 hours. Cambell reported to Admiral Hall. Sir, we have a solution. Spring-loaded striker bolt. Breaks sand's friction grip on the main hinge pins. We've tested it 5 times. Perfect success rate. Hall examined the mechanism on LCT 947. It looked crude, just a bolt and spring bolted to the side of the ramp housing. This looks like farm equipment, Commander. Cambell. Sir, farmers fix things that need to work, not things that need to look impressive. It works. That's what matters. Hall. Cost per boat? Approximately 2 pounds sterling, sir. Parts are off the shelf. Installation time, 45 minutes with trained crew. Hall calculated silently. 2 pounds sterling times 6,000 boats equals 12,000 pounds. To protect a $3 billion operation. How long to install across the entire fleet? Cambell. With sufficient personnel working round the clock, approximately 3 weeks, sir. We can complete the entire modification program by June 1st, 4 days before D-Day. Hall looked at the crude but functional striker bolt. Then at the calendar, 5 weeks to invasion. You have authorization. I'll get you every engineer, welder, and machinist in southern England. This is now highest priority. Whatever resources you need, you get them. Cambell. Thank you, sir. One more thing. This needs to remain quiet. If German intelligence learns we're conducting emergency modifications to 6,000 landing craft 5 weeks before invasion. Hall nodded. Operational security. Modifications will be logged as routine hydraulic maintenance. No technical details in reports until after D-Day. Cambell's team had proven the striker bolt worked. Now came the harder part, installing it on 6,000 ships in 3 weeks. And doing it secretly so German spies wouldn't notice that the entire Allied landing craft fleet was undergoing emergency modifications weeks before the largest invasion in history. The race had begun. Portsmouth, Southampton, Plymouth, Dartmouth, Falmouth. May 12th to June 2nd, 1944. Operation began 0600, May 12, 1944. Codename Program Sledgehammer. Internal designation, never widely used. The scale. Landing craft requiring modification. Approximately 6,000 vessels, LCT, LCI, and other ramp-equipped craft. Time available, 21 days, May 12th to June 2nd. Required modification rate, 286 boats per day minimum. The mobilization. Admiral Hall's authorization mobilized every available resource across southern England. Personnel assigned. Royal Navy Engineers, 840. U.S. Navy Seabees, 620. British civilian shipyard workers, 380. Total workforce, 1,840 personnel. Organized into 3 shifts. 24-hour continuous operations. Facilities. Portsmouth Naval Base, 12 modification bays. Southampton Docks, 8 bays. Plymouth Harbor, 10 bays. Dartmouth, 6 bays. Smaller facilities, Falmouth, Poole, Weymouth, 14 bays. Total, 50 simultaneous modification stations. The procedure per vessel. Step 1, vessel positioning, 15 minutes. Landing craft brought to modification bay. Bow ramp exposed for access. Step 2, installation, 45 minutes. 2 striker bolt assemblies installed, 1 per hinge pin. Mounting brackets welded to ramp housing. Striker bolts and compression springs fitted. Hydraulic release integration. Step 3, hydraulic testing, 20 minutes. System pressurized. Release mechanism tested. Dry cycle, no load. Striker timing verified. Step 4, load testing, 15 minutes. Full ramp deployment test ×3. Timing recorded, mechanism inspected. Step 5, crew training, 30 minutes. Boat crew briefed on modified system. Emergency procedures reviewed. Documentation completed. Total time per boat, 2 hours 15 minutes average. With 50 stations operating 24/7, theoretical capacity, 22 boats per hour. Daily capacity, 528 boats. 21-day capacity, 11,088 boats. More than adequate for 6,000 boats, if everything went smoothly. Week 1, May 12th to 18th. The modification teams faced a steep learning curve. Day 1, May 12th. Teams unfamiliar with procedure. Installation time, 4 hours per boat, too slow. Boats completed, 187. Status, behind schedule. Day 2, May 13th. Procedures streamlined. Installation time, 3 hours. Boats completed, 187. 264. Day 3, May 14th. Teams hitting rhythm. Installation time, 2 hours, 45 minutes. Boats completed, 312. Day 4, May 15th. Target speed achieved, 2 hours, 15 minutes. Boats completed, 389. Day 5 to 7, May 16th to 18th. Full efficiency operations. Average, 420 boats per day. Week 1 totals. Boats modified, 2,156. Target, 2,000. Status, ahead of schedule. The supply chain. Lieutenant Fraser coordinated parts production. Requirements. Striker bolts, 12,000 units, 2 per boat. Heavy compression springs, 12,000 units. Mounting brackets, 12,000 sets. Hydraulic coupling hardware, 12,000 sets. Production. British Steelworks, Birmingham, bolt stock. Sheffield Spring and Steel, compression springs. Local naval machine shops, mounting brackets. Timeline. May 12th, initial orders placed. May 15th, first deliveries, 2,000 units. May 20th, full production rate, 1,500 units daily. May 28th, all components delivered. Cost accounting. Parts cost per boat, £2 $8 times 6,000 boats equals £12,000 $48,000. Labor cost, 1,840 workers times 21 days times £1 50 daily wage. £58,000 $232,000. Total program cost, £70,000 $280,000. To save a $3 billion operation and potentially the invasion itself. Return on investment, approximately 10,000 to 1. Security measures. British intelligence, MI5, Coordinated operational security. Countermeasures. 1. Cover story. All modifications logged as routine hydraulic system maintenance and inspection. 2. Dispersed operations. Work spread across 50 locations. No single point of observation. 3. Communications blackout. No technical details in any written communications. 4. Restricted access. Modification bays declared off-limits except to authorized personnel. 5. Deception. Some maintenance performed on vessels not requiring modification to obscure pattern. MI5 monitoring of known German intelligence networks. No indication enemy detected unusual activity. German intelligence remained unaware that Allied landing craft fleet was undergoing emergency modification. Week 2, May 19th to 25th. Operations continued at peak efficiency. Daily average, 432 boats modified. Week 2 totals, boats modified, 3,024. Cumulative, 5,180. Target, 4,000. Status, significantly ahead of schedule. By May 25th, 86% of fleet modified. Week 3, May 26th to June 2nd. Final push to completion. May 30th, 5,850 boats modified, 98%. June 1st, 6,047 boats modified. June 2nd, 1,800 hours. Program complete. Final count, 6,089 landing craft modified. All primary invasion vessels, plus operational reserves. Total elapsed time, 22 days. Average daily rate, 277 boats per day. Program completed 3 days ahead of June 5th, D-Day date, subsequently postponed to June 6th due to weather. Lieutenant Commander Cambell's inspection, June 2nd. Cambell toured Portsmouth Harbor, walking among rows of modified landing craft. Each bore the modification. 2 small striker bolt assemblies, barely visible unless you knew where to look. Simple steel and spring mechanisms. Crude, inelegant, functional. Admiral Hall joined him on the quay. Commander, your team has just modified 6,000 vessels in 3 weeks. Do you understand what you've accomplished? Cambell, sir, we installed striker bolts. Now we need to see if they work under fire. Hall, they worked in testing. Cambell, testing isn't combat, sir. We'll know on June 6th whether we succeeded. Hall paused. I'm putting your team in for commendations after the invasion. Cambell, sir, I'd rather you just ensure the boats work when we need them. Hall smiled. They will, Commander, because you made certain of it. June 2nd, the fleet was modified. The bolts were installed. Testing showed promise, but in 4 days, 6,000 boats would hit the beaches of Normandy under German machine gun fire. Would the striker bolts work when it mattered most? Or would tanks still be trapped when the ramps needed to open? English Channel, June 6, 1944, 0530 hours. The largest armada in history crossed the channel toward France. 156,000 Allied troops aboard 6,939 vessels. Among them, 6,089 landing craft equipped with Cambell's striker bolt modification. The invasion's success depended on armor reaching the beaches. Armor reaching the beaches depended on ramps opening. In minutes, the striker bolts would face their ultimate test. Omaha Beach, Sector Easy Red, 0630 hours. LCT 947, Cambell's original test vessel, grounded on Omaha Beach at 0631 hours. German MG-42 machine guns opened fire immediately. Bullets ricocheted off the steel hull with metallic pings. Inside, 4 Sherman tanks, engines running, crews waiting. The LCT commander, Lieutenant Daniel Morrison, hit the hydraulic release. Clang, sharp metallic impact, striker bolts firing, hydraulic whine. The 3-ton bow ramp dropped forward onto the beach. Deployment time, 28 seconds from hydraulic activation to full open. First Sherman rolled out into 2 feet of water. Tracks gripped sand. The tank surged forward, 75mm gun traversing toward German positions. Second tank out, third, fourth. All 4 Shermans off the boat in 85 seconds. LCT 947 reversed, ramp raised, withdrew to collect the next load from the transport ships offshore. The striker bolts had worked under fire. 0630 to 0800. First wave across 5 beaches. Omaha Beach. LCT first wave, 47 boats. Successful ramp deployments, 44. Failures, 3. Utah Beach. LCT First Wave, 38 boats. Successful, 36. Failures, 2. Gold Beach, British. LCT First Wave, 41 boats. Successful, 36. Failures, 2. 40. Failures, 1. Juno Beach, Canadian. LCT First Wave, 35 boats. Successful, 33. Failures, 2. Sword Beach, British. LCT First Wave, 39 boats. Successful, 38. Failures, 1. First Wave totals. LCT deployed, 200 boats. Successful deployments, 191. Failures, 9. Success rate, 95.5%. Failure rate, 4.5%. Compared to Exercise Fabius, May 3rd to 8th, 73% failure rate. The Striker bolt modification had reduced failures from 73% to 4.5%. Improvement, 93%. Analysis of the 9 failures. Beachmasters and naval engineers examine failed boats when possible. Failure breakdown. Combat damage to hydraulics, 5 boats. Shellfire severed hydraulic lines. Structural damage from obstacles, 2 boats. Underwater mines damaged ramp housing. Crew error, 1 boat, hydraulics not properly engaged. Unknown, 1 boat, sunk before investigation possible. Failures attributable to sand jamming, 0. The problem Cambell's team solved, sand infiltration causing friction lock, had been eliminated. The remaining 4.5% were unavoidable combat casualties and human error. Allied Headquarters, Portsmouth, June 6, 1400 hours. Preliminary reports reached Admiral Hall from Beachmasters across all 5 landing zones. Summary: ramp deployment successful across all sectors. Minimal mechanical failures. Armor landing on schedule. Beachheads being established. Hall drafted a message. 2. Lieutenant CDR Cambell, HMS Belfast. From ADM Hall. Your Striker bolts performed as designed. Ramps deploying successfully all beaches. Armor ashore. Well done, Hall. HMS Belfast, off Sword Beach, 1430 hours. Lieutenant Commander Cambell received Admiral Hall's message. He read it once, folded it, put it in his pocket, then returned to the ship's rail, binoculars raised, watching landing craft operations. Boats hitting beaches, ramps dropping with that distinctive clang of Striker bolts. Tanks rolling out onto French sand, exactly as designed. The solution, simple, crude, rushed into production, was working. Thousands of times across 5 beaches, under fire, working. June 6 to 12th, continued operations. Over the following week, thousands more landing craft sorties delivered men and material to Normandy. Week 1 statistics, June 6 to 12th. Total LCT sorties, 4,847. Ramp mechanical failures, 184. Failure rate, 3.8%. Failure analysis. Combat damage, 122 failures, 66%. Crew operational errors, 35 failures, 19%. Mechanical failures, non-ramp systems, 21 failures, 11%. Sand jamming of ramps, 6 failures, 3%. The 6 sand jamming failures occurred on boats where Striker bolt mechanisms had been damaged by combat, springs broken by shrapnel, Striker bolts bent by explosions, mounting brackets torn off by direct hits. Undamaged Striker bolt mechanisms, 100% success rate against sand jamming. The counterfactual: what if the Striker bolts hadn't existed? Military historians have analyzed what would have occurred if Exercise Fabius's 73% failure rate had replicated on D-Day. First wave, 200 LCT. Expected failures at 73%, 146 boats. Tanks unable to deploy, approximately 584 Sherman tanks. Infantry advancing without armor support, catastrophic vulnerability. Likely outcomes, Omaha Beach. Complete failure to break off beach. Casualty rate potentially 40 to 50% versus actual 30%. Possible evacuation order. Other beaches. Severe delays establishing beachheads. Heavy casualties among infantry. German counterattacks more effective. Overall D-Day. Success highly questionable. Possible failure requiring second invasion attempt months later. Actual outcome with striker bolts. First wave, 95.5% success rate. 764 tanks successfully deployed. Infantry received armor support. Beachheads established. D-Day, success. The striker bolts worked. The invasion succeeded. But Cambell's story didn't end on June 6th, because after the battle, Allied intelligence discovered captured German documents. And those documents revealed something chilling. The Germans knew about the LCT ramp problem, and their entire defensive strategy had counted on it. Paris, France, August 25, 1944. Allied forces liberated Paris. Among the secured facilities, Kriegsmarine, German Navy, Intelligence Headquarters, Avenue Foch. British naval intelligence officers swept the building, collecting documents before they could be destroyed. In the technical analysis section, they found a report dated March 1944. Alliierte Landungsboote, Technische Schwachstellenanalyse. Allied landing craft, technical vulnerability analysis. The report, stamped Geheim, secret, contained detailed analysis based on landing craft captured at Dieppe in 1942 and subsequent coastal raids. Section 4. LCT Bug Rampen Mechanismus. LCT bow ramp mechanism. The German analysis identified testing of erbeutete LCT, captured LCT, demonstrates critical vulnerability in Rampenmechanismus, ramp mechanism. Infiltration of strand material, beach material, sand, kiesel, shingle, into charnier assembly, hinge assembly, creates Reibungswiderstand, friction resistance, exceeding hydraulische Kapazität, hydraulic capacity. Observed failure rate in realistic Übungen, exercises, 60 to 70%. Tactical recommendation. Defensive forces should permit Allied Landungsboote to strand ohne Beschuss, beach without fire. Allow Rampenbereitstellungsversuch, ramp deployment attempt. High probability of mechanische Versagen, mechanical failure, will result in trapped Panzer, tanks. Infanterie ohne Panzerunterstützung, infantry without armor support, vulnerable to konzentrierte MG-Feuer und Artillerie, concentrated machine gun fire and artillery. Defensive doctrine, conserve artillery fire for immobilized targets. Do not waste munition destroying landing craft at sea. Exploit expected mechanical failures. The German strategy. German commanders defending Normandy had received these intelligence assessments. Their defensive doctrine incorporated it. Let the landing craft beach. Don't expend artillery destroying them offshore. Let them ground. Let crews attempt ramp deployment. German intelligence predicted 60 to 70% of ramps would jam. When tanks were trapped, German guns would destroy immobilized targets. Infantry without armor support would be pinned on the beach. Then, systematic destruction with pre-sighted machine gun and artillery fire. The entire strategy depended on Allied equipment failure. What the Germans didn't know. In May 1944, while German intelligence was distributing their analysis, Cambell's teams were installing striker bolts across the invasion fleet. The modification program remained undetected. German defensive plans were based on intelligence that was accurate in March, but obsolete by June. Result: June 6th. German troops waited for Allied ramps to jam. Instead, ramps dropped successfully. Tanks deployed immediately. Armor broke through defensive positions faster than German doctrine anticipated. The expected mechanical failures never materialized. Captured German officer testimony. Oberst Fritz Ziegelmann, 352nd Infantry Division, Omaha Beach Sector, interrogated June 1944. We received intelligence reports indicating Allied landing craft had significant ramp failure rates. Intelligence assessment, 60 to 70% failure probability under beach conditions. Our defensive plan incorporated this intelligence. We were ordered to withhold fire on landing craft until they beached and attempted ramp deployment. The plan was to allow mechanical failures to trap their armor, then destroy immobilized targets with artillery. When the landing craft arrived at Omaha, we observed the ramps. We expected jamming. We expected trapped tanks, but the ramps opened. Almost all of them. Tanks deployed faster than our intelligence predicted. The armor came off the boats immediately. We were not prepared for this volume and speed of deployment. If the ramps had jammed as intelligence predicted, We could have held Omaha Beach, perhaps stopped the invasion at that sector. But their ramps worked, their tanks deployed, and we could not stop them. The intelligence failure. Why didn't German intelligence detect the modification program? British counterintelligence analysis, September 1944. The Striker Bolt program succeeded in remaining covert because 1. Speed of execution. 22-day modification window was faster than typical German intelligence collection to analysis to distribution cycle, 30 to 45 days. 2. Dispersed operations. 50 modification sites prevented pattern detection. German agents would need to observe unusual activity at multiple locations simultaneously. 3. Effective cover story. Routine hydraulic maintenance was plausible. Agents reported increased maintenance activity, but assessed it as normal pre-invasion preparation. 4. Communications security. No technical details in written communications. No leaks from 1,840-plus personnel involved. 5. Timing. Even if agents had reported unusual landing craft modifications in late May, reports wouldn't reach defensive units before June 6th. By the time German intelligence could have updated their assessment, D-Day had already happened. Post-war analysis. U.S. Army Historical Division. D-Day, Equipment and Logistics Factors, 1946. German defensive doctrine at Normandy beaches incorporated expectations of Allied equipment failure, specifically LCT bow ramp malfunctions. German intelligence assessments, based on captured vessels and observation of Allied training exercises through early 1944, correctly identified a significant vulnerability. 60 to 70% ramp failure rates were accurately documented. The Allied Striker Bolt modification program, May 1944, eliminated this vulnerability while remaining undetected by German intelligence. German commanders interviewed post-war confirmed their defensive plans included exploiting expected mechanical failures. The modification program denied German forces a tactical advantage they had specifically planned to utilize. Assessment. Striker Bolt program contributed significantly to D-Day success by invalidating enemy defensive doctrine based on outdated equipment performance assumptions. Lieutenant Commander Cambell, post-war interview, 1946. I didn't know the Germans were counting on our ramps failing. Our focus was solving a mechanical problem. If I'd known the enemy's defensive plan relied on our equipment breaking down, I suppose it would have added pressure. Perhaps it's better not to know how critical your work is until after it's done. We installed Striker bolts because ramps were jamming. That they happened to invalidate German intelligence and defensive planning, that was fortunate timing more than strategic planning. The Germans had counted on Allied technology failing. It didn't, because a team of engineers installed crude, spring-loaded bolts in 3 weeks. But the Striker bolt's importance extends beyond D-Day, because the lesson it taught, that simple, achievable solutions beat sophisticated, delayed perfection, would reshape military engineering for the next 80 years. And that lesson is still being learned today. Fort Belvoir, Virginia. 1947, U.S. Army Engineer School. The D-Day Striker bolt became required study. Course, Advanced Military Engineering. Design Case Study 7. Operational Urgency versus Engineering Perfection. The LCT Ramp Modification, May 1944. The curriculum taught. When Lieutenant Commander Cambell's team faced the LCT ramp crisis, with 5 weeks until D-Day, multiple engineering solutions were theoretically available. Sophisticated options. Redesigned hydraulic system, 6 months. Advanced protective sealing, 4 months. New materials engineering, 3 months. Complete ramp redesign, 8 to 12 months. Crude option. Spring-loaded Striker bolt, 3 weeks. Available time, 5 weeks. Decision, crude solution. Result, success. Principle. In military engineering under time constraints, the achievable solution that works is superior to the perfect solution that arrives too late. Corollary. Simple, robust mechanisms are often more reliable under field conditions than sophisticated, optimized systems. The philosophical evolution. Pre-World War II engineering philosophy. Optimize for performance. Complexity acceptable if it enhances capability. Post-World War II engineering philosophy. Optimize for reliability and maintainability. Simplicity preferred. Complexity only when absolutely necessary. The shift was driven by lessons like the Striker bolt, German engineering philosophy, exemplified by Panther tank discussed in earlier contexts. Maximize performance, accept maintenance complexity, assume support infrastructure will adapt to requirements. Allied engineering philosophy, exemplified by Sherman tank and Striker bolt. Ensure reliability under adverse conditions. Minimize maintenance complexity. Design for realistic support infrastructure limitations. One approach produced engineering masterpieces that failed in field conditions. One approach produced adequate tools that functioned reliably and won wars. Modern applications of the Striker bolt principle. 1. Apollo 13 crisis, April 1970. When Apollo 13's oxygen tank exploded 200,000 miles from Earth, NASA engineers faced CO2 buildup in the lunar module, a crisis requiring immediate solution. Sophisticated option, design new filtration system. Time available, approximately 20 hours before CO2 reached lethal levels. Simple solution, duct tape, plastic bags, cardboard, and sock. Materials available aboard spacecraft. Engineers chose simple. Astronauts survived. Same principle Cambell applied. When time is critical, the crude solution you can implement immediately beats the perfect solution that arrives too late. 2. Boeing 737 MAX MCAS system, 2019. Boeing faced an aerodynamic challenge. Larger engines on 737 MAX altered pitch characteristics. Simple solution. Redesign aircraft structure to accommodate engines properly. Expensive, time-consuming, requires recertification. Sophisticated solution. Automated software system, MCAS, to compensate for aerodynamic changes. Faster implementation, lower cost. Boeing chose sophisticated. Result, 2 crashes, 346 deaths, 20-month worldwide grounding, billions in losses. Lesson. The crude physical engineering solution would have been safer than the elegant software solution. Sometimes simple is not just faster, it's fundamentally more reliable. 3. SpaceX engineering philosophy, 2002 to present. Traditional aerospace, highly optimized, sophisticated, minimal redundancy, maximum performance. SpaceX approach, simpler designs, extensive redundancy, proven technology. Example, Merlin rocket engines. Traditional approach, highly sophisticated engine design, maximum specific impulse optimization, single engine configurations where possible, complex, expensive, difficult to manufacture. SpaceX Merlin approach, simpler design based on proven Apollo-era technology, multiple engines providing redundancy, good enough performance with robust reliability, mass-producible. Result, SpaceX achieves higher overall reliability through simplicity and redundancy rather than sophisticated optimization. Same principle, multiple simple components often more reliable than single sophisticated component. Military engineering evolution. Post-World War II, U.S. military incorporated what became known informally as the Cambell principle. Modern military design requirements explicitly include 1. Maintainability in field conditions. Repairs possible with basic tools. Minimal specialized equipment required. 2. Reliability under adverse conditions. Design assumes worst-case environment. Tolerance for dust, sand, water, temperature extremes. 3. Rapid modification capability. Modular design allowing field upgrades. Standardized interfaces. Examples. M16 rifle development. Initial design, sophisticated, tight tolerances, prone to jamming in Vietnam. Redesigned, more robust, better fouling resistance, simpler maintenance. Modern M4, further simplified, maximized reliability. M1 Abrams tank. Engine designed for rapid field replacement, unlike World War II German tanks. Modular component systems. Maintenance possible at unit level, not just depot. All reflecting Striker bolt lesson. Field reliability through simplicity. The fundamental trade-off. Every engineering design faces inherent tension. Performance, reliability. Sophisticated, simple. Optimal, adequate. In peacetime, you can pursue performance and sophistication. Time exists for testing, refinement, perfection. In wartime, you must prioritize reliability and adequacy. Perfection is the enemy of timely sufficiency. Cambell's striker bolt, not elegant, not sophisticated, not optimized, but reliable, simple, adequate, and achievable in available time. In war, adequate and timely wins. Perfect and late loses. The striker bolt saved D-Day, but Cambell himself remained largely unknown. No monuments, no popular histories, just a small display in a naval museum and a case study in engineering schools. Most people who know D-Day don't know about the engineer who ensured the tanks could leave the boats. But the soldiers knew, and they never forgot. Recognition and obscurity. Lieutenant Commander Dennis Cambell received Distinguished Service Order, DSO, British Military Decoration, Legion of Merit, United States Military Award, promotion to Commander. His team received various commendations, but outside military engineering circles, the striker bolt story remained largely unknown. No Hollywood films, no best-selling books, no monuments to the engineers who saved D-Day with springs and bolts. Popular D-Day histories focus on airborne operations, Omaha Beach casualties, Eisenhower's decision-making, weather delays, German defensive failures. They don't mention the 3-week sprint to modify 6,000 landing craft. Why? Because striker bolts aren't dramatic. Springs and hydraulics don't make compelling cinema. Engineering solutions lack the visceral impact of soldiers storming beaches under fire. But the soldiers knew. Normandy, France, June 1945. First Anniversary Memorial Service. Veterans of the 1st and 29th Infantry Divisions, Omaha Beach, gathered at a memorial service. A tank commander, Captain James Mitchell, 741st Tank Battalion, approached an officer in Royal Navy uniform. "Sir, are you Commander Cambell?" Cambell, "Yes, Captain." "Sir, I commanded the lead Sherman off LCT 947, Easy Red Sector, 0631 hours, June 6th. Our ramp dropped in 30 seconds. We got off that boat and onto the beach while the Germans were still acquiring targets. If that ramp had jammed, if we'd been trapped for even 2 minutes, German artillery would have destroyed us." Cambell, "Your crew did the fighting, Captain. We just made sure the ramp worked." Mitchell, "Sir, with respect, if the ramp hadn't worked, there wouldn't have been any fighting. Just dying. Your striker bolt got my tank onto that beach, got me home to my family. Thank you." Similar conversations repeated throughout the day. Tank crews, infantry who followed armor off the beaches, landing craft crews who operated the modified ramps. They knew what the striker bolts had done. They knew who to thank. Post-war career. Commander Dennis Cambell remained in Royal Navy service until 1952. After retirement, consulting engineer for commercial shipbuilding firms, specialized in hydraulic systems and marine cargo handling equipment. He never publicly discussed the striker bolt program. When asked about his DSO award, he would say, "Engineering work during the invasion, nothing dramatic." The Last Interview, 1979. A military historian conducting D-Day research discovered Cambell's name in declassified documents about the LCT modification program. He interviewed Cambell, then 70 years old, at his home in Portsmouth. Historian, "The documents suggest your striker bolt modification may have been critical to D-Day success. Do you agree with that assessment?" Cambell, "I think that's overstating it. The invasion succeeded because of thousands of factors: intelligence, planning, courage, weather, German mistakes. We solved one mechanical problem. Important, yes. Critical? That suggests if we hadn't solved it, everything would have failed. I'm not certain that's true." Historian, "But the exercise failure rates were 73%. If that had occurred on D-Day," Cambell, "If that had occurred, someone else would have found a different solution, or commanders would have adapted tactics, or soldiers would have improvised. Wars aren't won by single engineering fixes. They're won by thousands of people solving thousands of problems. We solved one problem. Others solved theirs. That's how it worked." Historian, "What would you want people to know about the striker bolt?" Cambell, "That when you're facing a crisis with limited time, don't pursue perfection. Find the simplest thing that solves the problem. Build it quickly, test it, deploy it. Perfect is the enemy of good enough. And in war, good enough, delivered on time, wins. Perfect, delivered late, loses. That's the lesson, not the bolt itself, but the principle behind it." Dennis Cambell died January 15, 1982, age 73. His obituary in the Times, London, mentioned his naval service and DSO award, but made no specific reference to the Striker Bolt program. Most readers wouldn't have known what he'd accomplished. National Museum of the Royal Navy, Portsmouth, UK, present day. In a modest display case, a single Striker Bolt assembly, recovered from LCT 947, preserved as a museum piece after the war. The placard, Striker Bolt Assembly, LCT Bow Ramp Modification, May 1944. This spring-loaded mechanism, designed by a Royal Navy engineering team led by Lieutenant Commander Dennis Cambell, DSO, was installed on over 6,000 Allied landing craft in 3 weeks before D-Day. The modification reduced ramp deployment failure rates from 73% to 4.5%. By ensuring reliable armor deployment on Normandy beaches, this simple mechanism, constructed from approximately 2 pounds worth of materials, contributed significantly to the invasion's success. Lieutenant Commander Cambell's principle: in wartime, adequate solutions delivered on time are superior to perfect solutions delivered late. Sometimes the largest victories depend on the smallest innovations. A few visitors stop to read the placard. Most walk past, heading toward displays of grand warships in dramatic naval battles. The Striker Bolt sits quietly in its case, simple, crude, unimpressive to look at, but responsible for getting thousands of tanks onto hostile beaches. Responsible, in its small way, for D-Day's success, the bolt that saved the invasion. History remembers the grand strategies and heroic battles. It forgets the engineers who made victory possible. But every time a simple solution saves a complex problem, every time pragmatism defeats perfectionism, every time good enough delivered on time beats perfect delivered late, the lesson of the Striker Bolt lives on. In engineering, in business, in life. Cost of Striker Bolt program. Engineering development, £0. Personnel already on naval payroll. Parts and materials, £12,000. Labor, £58,000. Total program cost, £70,000. $280,000 in 1944 dollars. Value protected. D-Day operation cost, approximately $3 billion. American and Allied lives, estimated, saved by reliable ramp deployment, 5,000 to 10,000. Strategic value of successful invasion, incalculable. Return on investment, approximately 10,000 to 1 in monetary terms, incalculable in human terms.